It's the same with heat. There are also three ways by which heat travels: convection, conduction, and radiation. Have you noticed how when you blow your hot chocolate, steam goes up? It is because the cold air that you blow pushes the hot air. The same happens while you're heating water. Although you're just heating the bottom part, it travels to the top. It is because when you heat a liquid or gas, the particles move away from each other so that the upper part becomes more compact than the lower, making the cold part sink and the hot part rise. This is called convection. How about when you touch a hot surface? The heat is transferred to your hand by conduction. Conduction is the transfer of heat between things that are in direct contact with each other. Another example of this is the transfer of heat from the stove to the pot. Now let's go back to the question that I first asked. Have you ever wondered how you can feel the heat of the sun even when it's far away? It's because the heat from the sun travels through something invisible. Like when you put your hand above something hot, you can feel the heat even without touching it. This is radiation. Now let's recap. Using a very common everyday activity, cooking. When you boil water, heat travels from the stove to the pot through conduction. Heat travels around the water that you boil through convection, and released heat to the surrounding air through radiation.
Earth's energy balance will enable you to understand radiative equilibrium. You will also be able to recognize that the temperature of Earth depends on the amount of solar energy that it absorbs. The temperature of Earth depends largely on the total radiation received from the Sun. The Earth reflects about 30% of the solar energy radiation reaching it and absorbs the remaining 70%. The absorbed solar radiation heats up the Earth. While the Earth continually absorbs solar radiation, it will not simply continue to heat up. In response to this heating, the Earth emits long-wave radiation into space. The emission of long-wave radiation cools the Earth. As the Earth cools, it emits less radiation to space, but because it is still continually absorbing solar radiation, it still heats up. As it heats up, the Earth emits more radiation to space, and so it cools. This dynamic physical process of absorption and emission and resultant heating and cooling creates what is known as a state of equilibrium. The term equilibrium describes a stable condition where all of the influencing factors are in balance and so cancel each other out. Because of this equilibrium, the temperature of the Earth has been relatively constant over time. For scientists, this balance between the amount of solar radiation absorbed and the amount of long-wave radiation emitted by the Earth is known as radiative equilibrium. Radiative equilibrium tells us that the long-wave radiation emitted by the Earth will equal the amount of solar radiation that is absorbed by the Earth. In fact, we can determine the temperature of the Earth by knowing the amount of long-wave radiation it emits. If one of the components of the Earth's energy balance changes the amount of long-wave radiation the Earth emits, the temperature of the Earth will also change, and the Earth will arrive at a new radiative equilibrium. For example, if the amount of solar radiation absorbed were to suddenly increase, the amount of long-wave radiation emitted would also increase. The temperature of the Earth would then increase, but a new radiative equilibrium would be reached, so the Earth would not continue to become hotter. In summary, the Earth's radiative equilibrium describes the balance between the incoming shortwave and the outgoing long-wave radiation. The temperature of the Earth can be determined by the amount of outgoing long-wave radiation, which is equal to the amount of incoming solar radiation absorbed by the Earth.
Hello and welcome. I'm Charlene and today we'll discuss reflection of light. On this show, we will help you not only get your physics fundas right, but also maximize your scores. We will discuss physics concepts, help you solve tricky problems, and give you many secret exam tips. Light is something that's everywhere. And the truth is, it is the only thing because of which we can see. Objects either emit light, or when light is thrown at them, they reflect light, and that is how we see things. Today, let's understand reflection of light and its laws, how light gets reflected from a plane mirror, characteristics of an image formed by a plane mirror, and we will make sure you crack your exams through our most awaited exam decoded section. Now, light, it is nothing but a form of radiant energy. When light falls on a body, it may either be absorbed, it may be reflected, or it may be transmitted through, when light travels through a medium like air and then encounters another solid or liquid medium like a man, a car, a book, or even water surface, most of the light, after interacting with the boundary separating the two medium, comes back to the first medium. This phenomena is called reflection of light. So in other words, reflection of light means that light waves are neither transmitted through nor absorbed, but are bounced back from the surface of the medium that they encounter. The ray of light approaching a reflecting surface, such as a mirror, is called incident ray. And the one that bounces back is called the reflected ray. An imaginary line drawn from the point at which the incident ray strikes and perpendicular to the reflecting surface is called the normal. The angle between the incident ray and the normal is called the angle of incidence, and the angle between the reflected ray and the normal is called the angle of reflection.
We have rods of different metals attached to a central hub. On each of the rods is a small amount of butter. The metal rods have different specific heats and will heat up at different rates. We will watch the order in which the butter melts. The aluminum melts first. The brass melts second. The iron melts third. The nickel melts fourth. The copper melts fifth. The stainless steel melts sixth.